Hey there, Calc folks, back here with another lecture where we're going to, we're wrapping up our application of integration here, folks. We're looking at our last section where we're going to look at some physical applications, some physics work that requires the application of integration. And what I have for you here in this lecture is a couple of quick setups for some physical application of the integration process, folks. I do give you the formulas and the proof, and these are rather fundamental cases, so I'm going to present a couple of them to you. The first one here you can see is the case for mass from variable density in one dimension. All right, we're not going to look at mass in higher dimensions quite yet. We're at least not with variable density over that higher dimensional space. We're going to look at just mass with variable density in a one-dimensional system. And you go, well, mass in one dimensions, that doesn't make sense because the way I understand mass is its density times volume. And I go, yes, that is correct. In our three-dimensional system, we do understand the mass of objects, masses of things that exist in our three-dimensional realm are described with respect to volume in the scientific world. But not always in our descriptions of density do we see a volume incorporation into that description. For example, in terms of volume, you might have a stone might be described to have a density of 200 pounds per cubic foot, right? Well, that works well for a stone, a three-dimensional stone. You have 3 cubic feet at 200 pounds per cubic foot. You have 600 pounds for that mass of that stone, right? Whereas something like a concept like carpet, maybe, where the carpet you'd put down on your floor, it might have a mass that's described with respect to its area. You might be told that it has a mass of 2 pounds per, 10 square feet, right? It weighs 2 pounds for 10 square feet, this material, this two-dimensional material, right? That would be a description of density that would come in the context of 2 dimensions. So if it's 2 pounds per 10 feet and you have 100 pounds of it, right? How many feet do you have? Well, that's going to be 50 times 10. That's going to be, 500 square feet of carpet if you have 100 pounds of carpet. Right? That weighs 2 pounds per square foot, or per 10 square feet. All right. Now, what we're going to consider, though, is this final case where we consider density defined in the context of one-dimensional space, and that's what we see here. Where density might be described as a mass measurement with respect to length. We might be told something like a pound per foot, or a kilogram per meter, right? Things that are described this way might be like carpet, not carpet, carpet's area, rope or cable, right? Or some thin one-dimensional, right, string, or maybe a metal rod, right? That's very small, right? That might be described with respect to its density along the length, as opposed to actual physical volume or even area, folks, right? So even though density is really a three-dimensional concept in our scientific realm when looking at the world around us, it at times is presented to us in not only three-dimensional descriptions, but 2- and 1-dimensional descriptions of density. And we're going to consider the cases for one-dimensional descriptions here. Mass with variable density in one dimension, right? And I do give you an example here of one-dimensional mass with constant density, and I just say consider a rope with a density is constant and described by 0.5 kilograms per meter, right? If the rope measures a length of 5 meters, then the mass of that rope is going to be 0.5 times 5, 0.5 kilograms per meter times the 5 meters, you get 2.5 kilograms for the mass of that object. And in terms of the labeling, you will see these mass labels cancel with one another. The units of mass cancel in this calculation, leaving you with just 2.5 kilograms for the mass of that length of rope. Now that's the case for constant density. We're looking at variable density. Right? The object has a variable density, right? The mass of the object is calculated with this integral calculation. Right? Suppose an object has a variable density described by rho equal to rho of x in one-dimensional space. Right? Then the mass of the object over lengths of x in this closed interval from a to b, right, is given by the calculation given by this integral. We are just going to integrate the density function over that length from a to b. And that is how we're going to calculate mass with variable density in a one-dimensional system. Yeah. Let's look at an example. These are rather straightforward, folks. Consider a rope with a density where the density with respect to the length is described by rho of x equal to the square root of 2x plus 5 kilograms per meter. Right? That's the density of our rope. It's described by, and it varies over the length with respect to x, where with respect to x, the density is the square root of 2x plus 5 kilograms per meter. Well, if we're interested in the mass of the rope over a length from 0 to 3 meters, right, over this length from 0 to 3 meters, over values of x in this interval from 0 to 3, then that mass calculation will just be the integrand of the, or the integral from 0 to 3 for the square root of 2x plus 5, all integrated with respect to the length x. How do we calculate this? Now, this is a little u substitution, folks. You're going to let u equal the interior 2x plus 5. That will imply du dx is 2, or 1/2 du will equal dx. So the dx will get replaced with the 1/2 du. The value under the radical will get replaced with the 2x plus 5. And then our bounds will be adjusted using the 2x plus 5 from 0 to 3 to 5 to 11. Plug in 0, you get 5. Plug in 3, you will get 11. Now the square root of u, its antiderivative, is 2/3 u to the 3/2 power. So the 2/3 and the 1/2 do cancel or simplify. Let me get back, jumping around here. The 2/3 and the 3/2, the 2's do cancel in the numerator and denominator there, simplifying to 1/3. And then 11 to the 3/2 power is just 11 times the square root of 11. And 5 to the 3/2 power is just 5 times the square root of 5. So this might simply be written as 1/3 times the quantity 11 square root 11 minus 5 square root of 5 in value. And that would be a measurement in kilograms. And that would be our exact mass of this rope over that interval of length. All right. Now, a little proof. These proofs are rather quick and straightforward. All right. What we do is we consider subdividing this solid that exists in one-dimensional space. For instance, we might subdivide our rope up into n sub-intervals. We might cut it up into little portions, n portions. Right? Where we can begin, we begin by denoting the length of each of those portions as b minus a divided by n. And we denote x sub k to be a value of x in the k subinterval of that solid, or sublength of that solid, right? We're going to allow it to be a value of x in that portion of the rope that we cut up, right? If we want to approximate the mass for the little tiny section of rope that we've cut up, or for this little portion of the solid, we could take its density at just some point along it at x sub k and get a measurement for kind of the average density over that rope and multiply it by its overall length, delta x, and we would get an approximation for that the density or the mass seen on just that small portion of this subdivided rope. Were to make that more exact, or to come up with, I should say, a total approximation of mass, you would add that up for each and every section of rope you cut your rope into. And to make that exact, you would start to subdivide your ropes into smaller and smaller and smaller subintervals. Right? Where you would look at the behavior of each as n heads off to infinity. the behavior of each of those summations as n heads off to infinity, and that's going to give you the exact mass of this calculation. And this should look familiar. This is the integration process at hand, where at this point we just apply the definition of the definite integral, where instead of having function little f, we have our function little rho. Right? And this limit of the Riemann summation involving rho converts right over to this integration involving rho of x. Right? This integration from a to b for rho of x dx. And that is our proof of this mass by variable density calculation, folks. All right? All right, folks. The second one I wanted to show you here. Let me bring this over. Let me go ahead and actually just save this one. Real quick, I'll go back in. This all 12 in size. Save, and we'll come back and print that out and include that with your lecture video here. The other topic we want to look at is work for variable force. And more specifically, we should say work for variable force in just simply our space, right? One-dimensional space here also, folks, where we understand that in one-dimensional space, a constant force of F is applied. If a constant force of F is applied over a distance of d, little d, the work done by the force is described by simply the force value times the distance. Measurement, right? The measurement of force times the measurement of distance gives us our measurement of work, right? Force times distance equals work in the case for a constant force being applied over a given distance, right? For example, consider applying a force of 16 newtons over a distance of 4 meters. And I already see my error here. Let me fix this real quick. If we apply 16 newtons of force over a distance of 4 meters, the work done by this force is described by the calculation 16 times 4. 16 newtons of force times 4 meters, right? We could even put our labels in there. 16 newtons times 4 meters equates to 64 Newton meters, folks. I had 16 in there. I don't know what I was thinking. But that does become 64 Newton meters. Where one thing we do note about a Newton meter is equivalent to 1 joule of energy when looking at the concept of work and energy. But in this case, we had the case for a constant force of 16 newtons being applied over a given distance of just 4 meters. All right? What we really want to consider, though, in this chapter, or this section of material, is what about the case for applying a variable force? What if the force you apply over that distance changes? And not only that it changes, not only does it vary, but it changes or varies with respect to the distance itself, where you happen to be at along the length over which you're applying this force. All right. Suppose a force varies with respect to the length over which it is applied in one dimensions, such that the force is described by the force function big F of x over values of x in this interval from a to b. Well, if this is our setup, the work done by the force over the interval of x is going to be described by the integral calculation seen here. We are just going to integrate our force function over all of those measurements of x in that interval of length from a to b. Right? We're going to add up all the infinite forces that are happening at every single value of x in this interval. And when we do that, we will get our calculation for the work in this case. All right? We could look at a quick example. These are quick, folks. I do look at a little U sub on this one too, just to have you practice in some U sub in your work. Suppose a force described by The force function 3x plus 1 raised to the third power newtons is applied in one dimension over values of x in the interval from 0 to 1 meters. Right? The work done by this force is described by the following integral calculation. We are just going to integrate our force function over that interval of x from 0 to 1. All right? And how we integrate that, I did kind of hint to the fact that we're going to do another u sub here. We might let u equal that quantity 3x plus 1. Right? If we let u equal 3x plus 1 inside here, then du dx will be equal to 3, implying 1/3 du will be equal to dx. And our integral can be rewritten into this form seen here. The 1/3 du replacing the dx value in our calculation. All right. The 3x plus 1 being replaced with this u, and then we can adjust our bounds from 0 to 1 to 1 and 4 using this formula and this relationship between u and x in our initial substitution. If we integrate u to the third, that bumps up to 4 in power, and we divide by 4, and 1/3 times a fourth is 1/12. Where when we evaluate u to the fourth across the bounds from 1 to 4, at 4 it's 256, and at 1 it's just 1 in value. So inside there we have 256 minus 1, which is 255. So we have 255 twelfths Newton meters as a measurement for the work being done here. All right? Force is in newtons, distance is in meters, so the interpretation for work is a measurement known as a Newton meter. And the integration leads us to 255 twelfths of a Newton meter. Now let's look at a quick proof. This proof is very similar to the one for the case of variable density. What we do is we just subdivide the length over which we're committing this force. Right? We're going to take the length over which we're going to apply this variable force, and we're going to subdivide that length up, that distance up, into little sub-distances or little sub-lengths. Delta x is going to be how long each of those sub-lengths are, and x sub k is just going to be a value of x in each of those sub-lengths. Right? And if we want to approximate the work done by the variable force f of x over the k sub-length, well, that's just going to rely on our understanding that work is force times distance, or it can be approximated in this case as force times distance. And the way we're going to go about approximating our force is we're going to look at the force at x sub k at a value of x in that k subinterval and kind of let that approximate the entire force over that subinterval. And then we're going to multiply by the length of that subinterval, and that'll give us the approximate work done over that little subinterval. Now, as always in these proofs, if I want to approximate the total work done, I add them up for all the subintervals of length. That's what we see happening here. Where to make that exact, we apply a limit as n approaches infinity, and we obtain this exact calculation seen here. Now, from the definition of the definite integral, little f gets replaced with big F in that definition, and that's it. Which means in the result given by that definite integral, we can replace the little f in the big F for our definite integral calculation of this work. And that is proof of the formula we see here. Now, I do want to take this one step further. I have one more example for you that fits in here. And there is a unique case of work done by a variable force, and it is described by Hooke's law for the case of a classical spring. All right? For the case of classical spring behavior. If we look at the definition, right? What is a classical spring is what's defined by Hooke's law. In the case of a classical spring, the force necessary to stretch or compress that spring a distance of x units is described by the force function f of x equal to k times x, where the value little k is what's known as the spring constant. Little x is how much we're going to compress or stretch, and it's the independent variable in our force function. And in the case of a classical spring, right? In the case of a classical spring, this is how we would expect the force to behave. in a very much a linear fashion with the spring constant over the length, x. All right? Now, that spring constant does vary from spring to spring, and really what it describes is the stiffness of the spring. The stiffer the spring, the larger your K value. The more force will be necessary to stretch or compress it a given distance. Right? That's going to lead to larger values of K. And we might look at an example to kind of consider this situation. And we might suppose a force of 6 newtons. Right? Suppose we apply a force of 6 newtons to a classical spring, and we see that spring actually compress 0.1 meters, or sorry, 0.01 meters, 1/100th of a meter. You apply 6 newtons of force. It takes 6 newtons to compress this spring just 1/100th of a meter. Right? We might be interested in determining the work done to compress the spring 0.25 meters. What is it going to take to compress it 1/4 of a meter? Right? If we know it takes 6 newtons to compress it 0.01 meters. All right? Well, to begin with, that information about how much it takes to compress the spring 0.01 meters, 6 newtons, can be used to actually calculate our spring constant. Right? From Hooke's law, we would be able to say that 6, this force, must be equal to that spring constant that we don't quite know, but we're going to figure out with this information, times the distance that we've compressed the spring, times x, 0.01 meters, or 1/100th of a meter. Where with this information and what we know about Hooke's law, we can solve this relationship for the value of K, the spring constant, and divide both sides by 0.01, or multiply both sides by 1 over 0.01, which is just really the reciprocal of 1/100th, which is 100. So if we take 6 times 100, that will give us 600 in value. And that is the value of the spring constant here. What does that tell us? We have a pretty stiff spring. That K is pretty large, right, in value. It took 6 newtons to compress it very little. So it's pretty stiff if you had to give a comparison, right, or just talk about stiffness. All right? Well, with that information about K, we can now go back and take note. So in this case, the force necessary to stretch or compress the spring x units will just be described by the force function f of x equals 600 times x. This force function seen here. Replacing the value of K we just calculated into the formulation given here by Hooke's law. For this specific case of a spring, this would be how we would describe the force necessary to compress or stretch it. We can see if we put in 0.01 here, we will get the value of 6. The newtons necessary to compress it or stretch it, that 0.01 meters. All right. So if that's the force function, I can use the force function to calculate this value for work. To compress it, 0.25 meters, right? I'm going to integrate over the interval from 0 to 2.5. And the work done compressing the spring 0.25 meters is given by this calculation here. W is going to equal, or work is going to equal, the integral from 0 to 0.25 with an integrand of 600x, and all integrated with respect to x. Where the antiderivative of 600x bumps the x up to 2, and we divide by 2, and we get 300. So it's 300x squared. 300 we could factor out as a constant multiple, but we evaluate x squared from 0 to 1/4, And that's just 1/16 in value. So 300 times a 16th is 316th Newton meters. And actually, we can start to reduce that. That'd be 158, right? We can even go further than that. That's 75 force of a Newton meter in value. If we want to make sure we simplify our fractions. All right? Good practice there, folks. So there's another work example. Another work example for the case of Hooke's law. All right? Where Hooke's law is describing the force necessary to compress or stretch a spring a certain distance. Right? A classical spring a certain distance. And in classical springs, that force is a linear force. Right? That force behaves in a linear fashion. Right? What would be less than classical would be a spring where the force does not behave in this linear fashion. Maybe it behaves in a square function fashion. Or maybe in an exponential or a log behavior. Right? Maybe we see logarithmic growth in the force. Right? There's a lot of different descriptions we could have for some sort of springy behavior. Right? But in a classical spring, it's defined by Hooke's law. All right? With that said, folks, I do have one more lecture in this chapter to get through. We have to look at just another case for physical application, and that's the case for lifting fluid objects. Like the case for removing all the fluid out of my cup here by sucking it out of a straw over the top lip. Or maybe looking at lifting a rope off the floor, or hoisting a chain over the top ledge of a building, or even lifting a flag from the floor up a wall, or lifting a banner up a building side, right? And maybe over the top ledge, rolling it up over the top ledge. Those are all cases for what we call lifting fluid objects. Certainly the case for a water, sucking water, pumping water out of a canister is lifting fluid objects, but those other cases are too. The one-dimensional case for a rope, the two-dimensional case for a flag, or the three-dimensional case for a fluid like a water, right? So, folks, that is where we have one other topic to talk about. That is a little grander. Try to get that video out to you as soon as possible, most likely before the weekend. And that'll wrap up our Chapter 6 material. And I do believe that's what we're going to test over here. We're going to probably save the Chapter 7 stuff for the next test. We will get into that next week, though, certainly. That'll be soon to come. We're not going to hold off on that because we do have a lot to get through in 7 and 8 before the halfway mark in the semester. All right. But that is our goal. And we're on track, and we'll keep on track here, folks. And I'll see you in class next time. Have a good one.